Now I'm going to show you an example with a data set that's built into a package called Sleuth3. That's from a textbook called The Statistical Sleuth. And in particular, this is a case study from chapter 8 of that textbook. Now, to figure out what this case study is about, I can look up the help page for it. So let's actually do that. Breakdown times for insulating fluid under different voltage. Okay, so I have different voltages that are applied to some kind of fluid. And then I have the time until the insulating property of the fluids broke down. So we're going to experiment by changing the voltage. That's what we are in charge of. We're in charge of the voltage. And then what we observe, the outcome variable, is the time until breakdown. Relationship between voltage and time. That's what we have. And I can summarize the data, because I usually do that when I get a new data set. And you can see that this data has 3 variables in it. It's got time and voltage, which we just talked about, and group. Okay, so I could have read about that in the help page, but it's common for lab data to have some kind of batching to it. Like maybe on each day they did a few more values. And I can look at the dimensions. So there's 76 rows here in those 3 columns. So let me make a plot of time against voltage. Here it is. So I made it twice. You know what I'm going to do? I'm going to go back to making just one plot at a time. There we go. Okay, so there's my plot. And so you can see, first of all, that as voltage increases, the time until breakdown tends to decrease, right? That's fine. But you can also see that this is not a perfect situation for a linear regression yet, right? If I try to put my mouse kind of in the mean time for each of these voltages that we experimented with, you can see it goes down according to a curve. And you can also see that the amount by which the points vary within each of these voltage groups changes a lot, right? When voltage is 26, look at this huge range in terms of the time. So when voltage is 28, big range. When voltage is 36 or 38, really small range. So we don't have equal variance. We also don't have linearity. So what are we going to do? Well, we could experiment with the different scenarios I just showed you. The one that's going to work here is the log of the outcome variable. So I've left the voltages as is, but I took the log of y, and look how nice this is. This is beautiful now, right? If I trace down the mean of this outcome variable given voltage, it's a nice straight line. The amount by which the points vary within each of these groups appears to be approximately the same. This is now really awesome. Okay, we're super happy about this. So I'm going to create those as variables that are just in the workspace instead of variables that are part of the data set, even though I usually would say that right here you should write case 0802 $ log time. Because I have to mention those variables a million times, this is a teaching example. I'm going to just create an object called log time that's a vector of all the log times, and an object called voltage that's a vector of all the voltages. And let me make a more beauteous graphic here. There we go. Okay, this is our graphic of log time versus voltage. I'm going to add to it the intersection of the means, just to recall our conversation about how regression is related to correlation. Remember that correlation is based on how often the points are diagonal from each other as opposed to adjacent. And you can see that's very much true here, that there's a lot of points here and a lot of points here and not so many on the other diagonal. And similarly, then that's reflected in the correlation. The correlation between voltage and log time is very strong. -0.7 is a strong correlation. And again, that's what we see in the picture, this diagonalness. So now I'm going to run a regression, log time on voltage, and I'm going to add the points from that regression to my graphic. And before I put them on the graphic, I want to just talk about them. So first of all, the points function, if you have not thought about this or seen this function yet, is like the plot function in that you give it x coordinates and y coordinates and it makes a scatter plot. But the difference between points and plot is that the points function adds those dots, that scatter plot, to whatever plot you already have. So you can't run points just all by itself. You run the points line and it adds those points to the existing plot. So what am I going to do? Well, my x-axis values are going to be this vector of voltages. On the y-axis, instead of plotting the actual log times, I'm going to plot the fitted values for log times. So for each voltage, I'm going to plot the point on the line that is predicted based on this model. Okay, so you can see I did that. I get these nice black dots. These black dots are the or tracing the line, I could connect them, but I'm purposely putting them in here as black dots because I want you to see that what the linear model implies is that for each voltage, we have a particular mean log time that we would predict. You can summarize that regression too if you want to, right? Just seeing that that summary comes up in the usual way. Okay. All right, I can also do it just by drawing the line right onto the plot. There we go, instead of with the black dots. Right, it's the same idea. Now, suppose that I wanted to make some intervals. Okay, so I'm going to go back to this same picture. All I've done is undot it here. So what I'm going to do here, and actually this is a lie, I'm going to edit this and repost it. This code doesn't show two ways. This code shows one of two ways. Sure. And I have another code file that shows it the other way. This code shows one of two ways to calculate the width of confidence bands. So in this code, I'm expressly going to calculate the values that you need in order to have the width of a confidence band. The other way to do it is to directly use the predict function, and I'll show you that in a different code file called helpwithpredict.r. So to make the confidence bands, remember the confidence band is going to be for each voltage. Let's come up with a confidence interval for the mean log time. So each of these different voltages is going to have a different confidence interval, and then if I connect the dots, those are called confidence bands. So what am I going to do? Well, here I'm just calculating sigma, my estimate of sigma, and then I'm going to calculate the standard error of each of those confidence, or each of those estimated means. Okay, and here, this what I've highlighted here is just exactly copying off the expression for the confidence interval for the predicted mean that I wrote on some slides. And then I'm going to come up with, so if you look at that, let's see what this SE1 thing is. Notice that it's a vector of 76 different numbers, because for each different data point, I've calculated what the standard error would be. So when the voltage is 26, and we're thinking about this data point, here's the predicted mean, and there's a certain confidence interval that the linear regression implies for that predicted mean. Right, when the voltage is 28, here's one of the values, right? For that value, here's the predicted mean, and we have a certain confidence interval. For this data point, same predicted mean, same confidence interval. So the confidence intervals, of course, will be the same for each of the dots that have the same prediction. So if you're thinking of this dot, there's a prediction for this mean. If you're thinking of this dot, there's a prediction for this mean. But the way this is coded right now, each of these different data points is going to give you the prediction of the mean of log time, and also the interval. So this SE1 is the standard error for the predicted mean for each data point. And then what am I doing here? I'm going to generate a vector of lower bounds and a vector of upper bounds, so that for each data point, I'll have the interval corresponding to the predicted mean, again, for that data point. So how am I going to do that? Well, here's the vector of fitted values. So that's the vector of the points on the line. And I'm going to subtract 2 times the standard error. Now, I'm not exactly subtracting 2. This data set is pretty small, and I wanted it to match the output that comes automatically from R. So instead of using 2 here, I'm actually finding the exact correct value from the t-distribution, which is 1.99. You can see why I usually use 2. It's very similar, right? 1.99 is a lot like 2. So if I run both of these, you can see LB1 is a vector of 76 different possible different values for the lower bounds. For each data point, LB1 gives you the lower bound of the confidence interval for a predicted mean, and UB1 gives you a vector of those upper bounds. So what I need to do is add the LB1 and the UB1 to the graphic, right? That's what I want. I want to have these bands of intervals. I want to plot the confidence interval for each different voltage and then connect the dots to make bands. So what I'm going to do here is use the points function, because I want you to see that I don't want to just make a new plot, right? I don't want to make a new plot. Instead of making a new plot, I want to add these points that I'm going to connect for the confidence intervals to my existing plot. So it's important that I have points here instead of plot. In addition to that, I have to order the data points. I have to order the data points by voltage, okay? Because if I don't, then I might connect the dots in the wrong order. So let me do this for a second. If I do, let's do something temporary. If I do points and then voltage and then LB1, just like that, you can see here's the lower bound. All I did for now is draw a dot, the lower bound in each of those places. And these lower bounds do not exactly fall along a line. They're actually a curve, because remember, we have more uncertainty about the points that are further from the middle. So the intervals are going to be a little lower. Now, to make the band, I want to connect these dots, okay? But note that if I don't connect them in order, I'm going to be not going here to here to here to here, but here to 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 here. It's going to be a huge mess, okay? And the more curvy these points are, the bigger mess it's going to be.